coding as such, the encoding process assigns certain code for all these voltages. Okay, that means what? For a voltage of 0.2 volts as an example case, I will be assigning certain code. For example, 001. Okay, for a voltage of 0.4 volts, I will be assigning other code. For example, 010. Okay, something like that. For a further voltage, I will be assigning 011 and so on. So it will be in this particular way. Okay, so the assigning of these particular codes to each standard amplitude is referred to as the process of encoding. That is the important thing to understand. What is encoding? Because quantizer and encoder, okay, understand the distinction. Quantizer simply produces standard voltages. Encoder assigns codes to this particular voltages. Okay. Now for the 8 levels, I will be having as an example case, I can have this, that 00, in this slide you can see this 000, 001, 010 and so on up to 111. Okay, you can have the representation for the 8 quantization levels. If I am having it higher, I can have higher bits per sample, that is number of bits per sample. If it is 16, I will be having from 0000 to 1111. Okay, understand this particular encoding process well. Now here in this particular slide, okay, one can see the sample example of a pulse code modulation scheme. You have now got the understanding of what is a pulse code modulation scheme. In that case, we are having first block sampling, second block quantization and one more block encoder. Okay, having seen what are these particular blocks, okay, what is the output of this finally is that the final thing output is simply a stream of bits. What is the shape of the output? Is simply a stream of bits, ones and zeros. Okay, 011, 00, 1001, something like that. You can have that particular sequence. Okay, so in this particular case, that is the shape of a PCM signal. That means simply a pulse train. Okay. Now see this particular slide, that in this particular slide one can see that analog voltage has got certain range, some specified range, but the overall value of the amplitude range is 4 volts. Okay. Maximum frequency FM is taken as a 3 kilohertz. Okay. If now you are having the L value to be 16, then in that case you are having bits per sample is equal to 4, as we have already seen it. 16 standard levels will result in 4 bits per sample. Okay. The sampling frequency here is say 8 kilohertz. How you are having the arrival at the 8K frequency is with the help of 2 higher than 2 FM. That means 2 into 3K is 6K, and higher than this standard value of the sampling frequency is 8 kilohertz. 8 kilohertz means what? 8,000 samples in 1 second. Okay, understand this, that in 1 second you are going to have 8,000 samples. So how fast it is, imagine. Further, now it is going to result in this particular rate that you are having RB. Okay, one can see in this particular slide that RB is finally going to be N into Fs. Okay, N into Fs. So that is 4 into 8,000. Okay. Now step size evaluation is overall value amplitude range is 4 volts upon L, that is L value is 16. So it is resulting in the step size of 0.25 volts. What is the error? Maximum quantization error is step size upon 2. Okay. And what is the required spectrum? Is equal to half of the RB bit rate, half of RB, that is the required spectrum. So in the slide you can actually see this particular figures. Now the disadvantages we have already seen, that the spectrum requirement is much higher, as we have seen. Then in case of this particular scheme, you are having step size is same throughout. Okay, in this case, if step size is same, as an example case, if you are having the step size same, okay, what is the result of this is that smaller amplitudes will have the effect of higher errors, that means quantization errors. Okay, smaller amplitudes will also be facing the higher errors. Okay, the effect of this is that the smaller amplitudes will be worst affected with the help of the higher quantization errors in case of the if you are having the step size remaining same. That is why if I am having this particular heavy quantization error for the smaller values of the amplitudes, then what is the result of this? It will be resulting in the distortion in the on the receiving side. Okay, so what you should have now, what is the remedy for this? Is step size should be smaller for smaller amplitudes. Okay, if you are having step size smaller, then in that case quantization error will also be small for the smaller amplitudes, and so SNR for the smaller values of the amplitudes will also be good one. Okay. So here you are having the process of conversion of the smaller amplitudes into higher amplitude ranges. Okay. So conversion of smaller into higher values of the amplitudes is the important solution for this particular problem. Okay. So in this particular slide you can see that smaller values of the amplitudes are offered with higher gain, okay, and higher values of the amplitudes are offered with the smaller gains. Okay, this can be seen with the help of this particular plot in the slide. Compounding process is what is this particular process called as. Okay. So smaller amplitudes are now going to occur in the higher strata of the amplitudes. So here also one can see the similar kind of a graph, okay, the compounding plot, that smaller signal resulting in the higher amplitudes. Okay, and you are having two internationally standard laws for this. Okay, that is two important laws are A law and mu law. Okay. And one can see that the output of this particular scheme is simply the ones and the zeros. So you can have the good representation with the help of this particular slide. Okay. And digitization also is shown, that I have already explained you with the help of the examples, that how do you have the process of digitization of a speech signal. This I have already explained you, multiplexing, that you can use a single path to transmit multiple signals. Okay. Then 8,000 frames in a single second. Okay. So one is having this particular kind of the standard existing in the case of the multiplexing. This I have just simply shown it to you for reference, that you can have such higher bit rates in the practical scene. Then you are also having the hierarchy of this particular processes, multiplexing processes 1.5 Mbps, 6.3 Mbps, 44 Mbps and 274 Mbps and so on. Okay, hierarchy of multiplexing. Okay. And this is what is the schematic shown, okay, for the fundamental scheme. Okay, in that particular case you are having some transducer and then ADC, then error correction is done, and then finally you are having the process of the transmission with the help of the analog again, because digital signal you cannot transmit it as it is in the space. So you are required to have the conversion from digital to analog again finally. So one can see in this particular slide that you are required to have all the processes again, opposite processes as compared to the transmitter on the receiving side also, okay. And finally you reproduce the analog 1 signal with the help of the output transducer, for example here in the speaker, okay. This is finally what is a quick recap. We have seen all these particular statements in this particular session, okay. Advantages, disadvantages, etc. We have studied 3 processes in PCM: sampling, quantization and encoding, okay. Then we have seen the digitization of the speech, okay, and so on, and then finally the multiplexing process in case of the digital signals. It is easier to have this particular processes in digital signals. Thank you all for the patient listening, okay. Any questions from the audience? Any questions from the audience? Any questions from the audience? Okay, we shall stop now. Good day to you all.